Hey everybody, this is Dr. Gowenstein, and in this video, we're going to do a calculus review. Okay, so calculus is a very important subject in mathematics, but it has so many applications. And in fact, it's used quite a bit in economics and even in data analysis. And so this calculus review will be very helpful for you. We're not going to do a comprehensive calculus review. We're really just going to touch on a few key concepts and techniques that will be applicable to your work in the program. Okay, so first what I want to do today is I want to talk about the concept of a derivative, or taking the derivative of a function. All right, I want to talk about that. And then I will go through how to take the derivative of a function. All right, so we'll talk about taking the derivative of a function. All right, so I want to talk about it conceptually, and then I will show you how to take the derivative of a function. All right, so there's a number of different rules there for how to do that. Okay, so you'll remember from the last video this idea of a function. Function takes some variable as an input, and it spits out an output. All right, and you all might also remember from last time we drew a graph. All right, um, a function, we can think about a function graphically. A function takes in an input, so x, and it spits out an output y. So let's say we had a function like this. All right, it's just showing this graphically. Okay, now what the derivative of a function is the derivative tells us what the slope of the function is at any particular point. All right. The derivative tells us what the slope is of a function at any particular point. All right, let me say it differently. What the derivative of a function is, all right, the derivative of a function tells us how the output, so how y changes as the input x changes. All right. So to what extent or how much does y change when x changes? All right. That's what a derivative tells us. A derivative of a function is actually also a function. The derivative of a function is also a function, and what that derivative function tells us is how y changes when x changes, or how y changes at a particular value of x. All right, so let me kind of explain. All right, so if we have a function x, or a function f of x, all right, when we quote take the derivative, you'll hear this terminology, take the derivative. What we're going to do is we are going to calculate what is written as this, right? This is how we write it. All right, if I'm taking the derivative of f of x, I will write this. This is the notation. You'll see this is kind of like a D. It's kind of a cursive or Greek looking delta. So delta or D. All right. So it's delta f of x divided by delta x. That's the notation. This is the notation for a derivative. All right. This is the derivative of, oops, huh? This is the derivative of f of x. All right. And the derivative of f of x tells us how f of x changes when x changes. All right. And so you actually kind of get the intuition of it. This Greek letter delta here, what this is saying is, or it's notation for change. So what this is basically saying is that the derivative is the change in the function given a change in the variable. All right. So it's change in f of x given a change in x. That's what the derivative tells us. That's actually really important to kind of pick up on that, because when we do data analysis, for example, sometimes in data analysis, what we're going to try to measure is how one economic factor or variable, how it changes when some other economic factor or variable changes. And so, in a way, when at least some of the data analysis that we do is very much trying to get at this idea of a derivative. It's understanding how one thing changes when something else changes. How does the function change when the variable changes? Okay. Now, a little bit earlier, I mentioned the idea of a slope. All right. So if we look at this line here, this line, this graph, you might recognize this. Just a straight line, and so you might recognize this from kind of early algebra, where you know the equation for a line is y equals mx plus b. That might ring a bell to you. If this rings a bell, we know y, that's the output of the function, right? The output. All right, x, this is the variable, this is what's changing. All right. You'll remember b, this is the intercept, or we sometimes we'll say the y-intercept. It's the point where the line crosses the y-axis when x equals 0. And you'll remember that m, this is the slope. Now, what we know about the slope of a line is the slope is how y changes. So the slope is how does y change when x changes? Right? That's the slope. How much does y change when x changes? Especially when x changes by 1 unit. All right, that's the slope. So you can see there's a close relationship here between the idea of a slope and a derivative. All right. So that's the idea behind a derivative. All right. Now there's a lot in calculus, but one of the major kind of subfields in calculus is taking derivatives or understanding the derivative of a function. And that's the only thing we're going to talk about in this video is taking derivatives. All right. That's the only thing you need to know. The other area of calculus is integral calculus. You don't need to know that. So I'm just going to talk about derivatives. Okay, so here's the idea. When we take a derivative, we are understanding how something changes when something else changes. All right, this is going to be very important. All right, so um, let me go through. What I'm going to do is I'm going to talk about some rules for taking derivatives of functions. All right, and I'll just kind of show you those rules. And as I show you those rules, I'll kind of continue to reinforce this basic understanding of what a derivative is. All right, it's important for you to understand the concept just intuitively to feel comfortable with it. It's also important for you to learn the tools for, quote, taking a derivative. All right, so let's learn the rules for taking derivatives. So first, let me just kind of write out a function for you. Maybe this can be a function that we will use as a template. All right, so let's say we have a function. I'm just going to make a simple one, 2x squared plus 5. All right, that's going to be my function. 2x squared plus 5. Okay, so here's a function. And as the variable x changes, all right, the value of this function will change. All right. The derivative of the function will tell us how much does f of x change when we change the value of x, right? That's what it's getting at. That's what it is telling us. It's telling us how much it changes by when x changes. Okay. And so we can take the derivative and actually figure out what that is. All right. Now, how do we take a derivative? How do we take a derivative? Okay. There is kind of the first step is to learn what is the basic formula for taking a derivative. To understand the basic formula for taking a derivative, let me write a function in generic format. Okay. Functions will oftentimes have this format. You'll have some parameter times a variable. The variable is raised to some power, some exponent. Okay. So let me just say that this is a kind of generic structure for what a lot of functions will look like. And this is super helpful. It's super helpful to recognize this structure in terms in a function. I'll explain it in detail in a minute. I'll kind of help you to recognize it. All right. If you have a function that is formatted like this, a function that looks like this, the derivative, right, the derivative of that function with respect to x will always be equal to this. B times A, right? So you'll see here what's happening is the exponent comes down, all right? And then you have the variable, and then you have the exponent minus 1. This is the basic structure of taking a derivative. If you are able to recognize this structure to a function and then just apply this formula, you are well on your way to taking derivatives of any function that you need to take a derivative of. All right, it's that simple. And even without fully understanding kind of the concept of what derivatives are in principle, if you need to take a derivative, this formula, this simple procedure is will get you 50 to 60% of the way there. I mean, this is the formula for taking derivatives. And all you need to do is pattern recognition, understand what is what in a function, and then just apply this formula. So let me give you an example by taking the derivative of this function I wrote out a moment ago. All right, so here we have the function is 2x squared plus 5. All right, I'm going to take the derivative of that using this formula. All right, so I'm going to take the derivative of it with respect to x. You'll notice I'm taking the derivative of it with respect to its variable. Okay, so one thing you'll do when you take derivatives is you will look at the function that you're taking a derivative of, and you will break it down into its separate terms. We talked about this in the functions video. You'll now see why it's so important. This function has two separate terms. What we're going to do is we're going to take the derivative term by term. So when I look at this function, what I'm going to do is I'm going to first stop and I'm going to look at, maybe I'll keep this. I'm going to look at the 2x squared first, and I'm going to take the derivative of that. Now, when I look at 2x squared, I'm going to notice that this 2 here, that's the a, right? The x is the x, that's the variable. And the 2 up in the exponent, that's the b. All right, so then all I need to do, now once I've figured out what a is and what b is, now all I have to do is just simply apply this formula to it. So let me do that. So b, right, b is 2, so here's 2, times a, right, again, a is 2, so 2 times 2. Then we have the variable times x, and then the exponent is b minus 1, all right, so b is 2, so 2 minus 1 is 1. All right, so there's our derivative, and we can simplify that. 2 times 2 is 4. And x to the 1 power is just x. So there we go. There's the derivative for the first term. Okay. And then we will go and do the derivative of the second term. Okay. So here's the second term. We have 5, and there's no x there. It's just the number 5. What's the derivative of the number 5 with respect to x? Well, I can tell you I can just kind of give you the answer real quick, and you're free to just learn this. If you encounter a term and that term does not have the variable, if you encounter a term and that term does not have the variable, then the derivative is just equal 0. So this 5 it doesn't have x in it, so the derivative is just 0. The derivative is just 0, which means, all right, the derivative of the second term is 0. We don't need to write 0 anymore. And so then we have our final answer. Our final answer is the derivative of f of x with respect to x is equal to 4x. And there we go. There's our derivative. So if we want to know, how is the function f of x changing given a change in x, a 1 unit change in x? This derivative will tell us. So basically what this is saying is that the function f of x is increasing by the value of 4x at any given point in the function f of x. That's how much it's changing. That's how the function f of x is changing given a 1 unit change in x. Okay. All right. So that is taking derivatives. Let me do another example just to kind of get practice with the basic structure of taking derivatives. All right, I'm going to write out a longer function here. So here's my function, 4x cubed plus 5x squared minus 10x plus 17. All right, just made that up. All right, and remember our basic formula. If we have f of x equals a x to the b, then the derivative of f of x is equal to b times a x to the b minus 1. And remember, what we're doing when we take derivatives is we're learning how functions change when the variable changes. Okay. All right, so let's just do this as practice. All right, I'm going to take the derivative of f of x with respect to x. All right, I'm just going to go term by term. Remember, so here's a term, here's a term, here's a term, here's a term. I'm going to go term by term, taking the derivative. Okay, so here I see that, here I'm going to pull out another color. So here I see that the 4 is the a in this term, and the 3 is the b in this term. The 5 is the a in this term, and the 2 is the b here. The 10 is the a here. And in this case, b is just equal to 1. All right, and you can see there's no x in this final term, so we know what to do there. All right, so let's just follow the math. 3 times 4 is 12. X raised to the b minus 1, so that's 2. All right. Here, b times a, so 2 times 5 is 10, times x to the b minus 1 power. So here's 2 minus 1. So that just becomes 1. We don't need to write the 1 because x to the 1 is just x. All right. And then here we go. So b is equal to 1. So 1 times a, that's negative 10. All right. Then we'll write x. And then b is equal to 1. So b minus 1 is equal to 0. So this is x to the 0 power. Does anyone know what x to the 0 power is? I'll just write this rule over here. X to the 0 power is just equal to 1, actually. So we can just delete this. All right. And then we get to the 17. Okay, look, there's no x. So the derivative of 17 with respect to x is just 0. So then it's done. We don't even write that. The derivative of this is just 0. So there we go. Here is our derivative of that function. All right, so this is the basic rule for taking derivatives. This is super important. Sear this in your mind. Kind of get comfortable with recognizing how functions are written like this, and then just simply apply the rule. When you're first doing derivatives, you might have to take your time and figure out, okay, what is A and what is B? Maybe I'll do one more example, maybe a slightly more complicated example. Here's f of x. So let's imagine we had somewhat of a complex question here. So what if we had a, I'm going to start using some generic parameters here, a plus b squared times x raised to the c minus d times a over 2 power. That's all up in the exponent. And you might look at that and you're like, oh my goodness gracious, what do we do with that? That's weird. That is a weird looking function. Well, first we just need to figure out what is a, right? Here's our generic functional form, a, x to the b. So just look at this and we say, okay, well, what is a? You know what? Here, let me pick some different letters. Let's say this is um, E and G, just for fun. All right, there we go. All right, so what you're going to do is you're going to look at this and you can say, well, what is A? Well, A is just this whole thing, this whole kind of ugly looking thing here. And then what's B? Well, B is uh, this kind of big ugly thing here. Oh, A is showing up here again. Let's change that. Um, let's just say H. Okay. Okay. All right. So we just figure out what A and B are and then follow the formula. So here's the formula, right? The derivative of f of x with respect to x, right, is b times a x to the b minus 1. So we just follow that structure. So even though it's going to be kind of large and clunky looking, there really is nothing to it. All right. So that's here we have a times b. All right, all of this, so this whole thing times x raised to the b, right? This is our b minus 1. That's it. It's a little clunky looking, right? So it's not, it doesn't strike us as being particularly elegant, but that's okay. As ugly as the function is, we just simply follow this structure, and that'll give us our derivative. All right. So here we go. That is a basic introduction to doing derivatives. Now what I want to do is I want to teach you a few rules for handling some slightly more complicated derivatives. Okay, so you have the basic structure, and now I just need to teach you a few rules that will help. All right, so the first one, um, so here's the first rule. So let me write this. I'm going to write this in a generic format. I've actually already showed you this one, but I just didn't give it by name here. Sorry. Um, so here is the addition, and also you could say the subtraction rule. Okay, so here when you are looking at a function, so let's say here we have a function, and the function is composed of separate terms that are added or subtracted from each other. So let's say we have some function x, and it's equal to some smaller function g of x plus, or it could be minus, some other smaller function h of x. So these are just other functions. I'm using different letters to represent the fact that they're different functions. That the derivative of f with respect to x is equal to the derivative of g with respect to x plus or minus, whatever that happens to be, the derivative of h of x with respect to x. We've actually already seen this. This is exactly what we did when we looked at this previous example. So in this earlier example, this was some function, we could call it g of x. And this is some smaller function, we could call it h of x. And this is some smaller function, and we could call it j of x. And here is some other function, and we could call it I of x. Okay, so these are separate functions, and when separate subfunctions or separate smaller functions are just added up or subtracted from each other, all you do is take the derivative of each one of them separately and then add or subtract them according to whatever the sign is, and there you have it. All right, so that's a very simple rule. In fact, you've already seen it in this lecture. That's the addition of the subtraction rule. All right, so the next rule is the product rule. Okay, so imagine we have the function f of x, and the function f of x is composed of two smaller functions, just like before. So just like we had g of x and we had h of x, right? Those are kind of our smaller functions within the larger function. Okay, so if we have a function and it is some function g of x times some other function h of x, in this case, we need the product rule. All right? When we have a function, and that function is composed of two smaller functions multiplied together, we need the product rule to take the derivative. So let me show you what that looks like. So the derivative of f of x with respect to x is equal to the derivative of g with respect to x times h of x plus the derivative, actually I should write it like this, plus g of x times the derivative of h of x with respect to x. That is the product rule. Okay, so let's do an example of that, kind of show you what I mean. All right, so here's an example. Here's f of x, all right, and let's say um, we have some function, let's say 4x plus 2, all right, and this is multiplied by 5x squared. So we have two functions. What are those functions? Well, g of x is equal to 4x plus 2, and h of x is equal to 5x squared. All right, we can just see that we have two terms here. We can see them as separate functions, but they're multiplied by each other. All right, so in this case, we can use our product rule. So let's go ahead and do that. All right, all we have to do is just remember what g of x is and what h of x is, and then we'll just follow the formula. All right, so let's do that. The derivative of f of x with respect to x, all right? So that is equal to the derivative of g times h, all right? So let's come over here. What is the derivative of g? All right, when we look at that, we can see the derivative of g of x is actually just equal to 4. All right, and then we're going to multiply that by h of x, so 4 times 5x squared, all right, plus g of x, right? So again, we're just following the formula, g of x, so that's 4x plus 2, and there's g of x, times the derivative of h of x. So let's do that. We can look here, here's h of x. We can do that derivative, that's 2 times 5 is 10, times x, right? And then 2, that's the b, minus 1. So 2 minus 1 is 1. We don't need to write the 1 up there. So there we go. There's the derivative. We can simplify it. So 20x squared plus 4x plus 2 all times 10x. If we wanted, we could simplify it even further. Just keep simplifying it until it's kind of fully simplified. We can distribute this 10x. Let's do that. So that would be 40x squared plus 20x. All right, so this becomes 60x squared plus 20x. Okay, so there's our derivative using the product rule. All right, so let's come over here. All right, the next rule that I want to look at is called the quotient rule. All right, quotient rule is going to be a very similar structure. We have some function f of x, and it has two subfunctions. g of x and h of x, just like before. All right, except in this case, g of x is in the numerator and h of x is in the denominator. All right, and so if we have a function that looks like this, we can use the quotient rule. Okay, so the quotient rule is derivative of f of x with respect to x is equal to the derivative of g with respect to x times h of x minus g of x, forget the of x here, times the derivative of h of x with respect to x, all divided by h of x squared. All right, this is definitely kind of the biggest and most complicated of the derivative rules. Um, but again, you follow the same structure. You just look at the original equation, figure out what g of x is, figure out what h of x is, and then just follow the formula. All right, so let's do an example. All right, so let's say we have f of x here, and all right, here's f of x. Let's say we have 4x squared divided by 5x minus 2. Let's say that is our function. You'll notice here, we can just label this, right? You'll notice that you have a function in the numerator, so that'll be g of x, that's equal to 4x squared. And we have a function in the denominator, so that's h of x equals 5x minus 2. All right. And so once we figure out what g of x is and what h of x is, we will just follow the equation. So let's do that. All right. So the derivative of f of x with respect to x is going to be equal to the derivative of g of x. So that's just 8x times h of x. So 5x minus 2. All right. All that minus g of x. That's 4x squared times the derivative of h of x, which that's just 5, all right? And then all of that is divided by 5x minus 2 squared. And we can simplify this a little bit, especially the numerator. Let's simplify the numerator. We'll distribute this 8x here. So we have 40x squared minus 16x minus 20x squared. All right. Same denominator. All right. And we can simplify that one more step. 20x squared minus 16x divided by 5x minus 2 squared. Okay. You notice here I switched from brackets to parentheses. There's actually no difference there. So, okay. So there we have it. That is using the quotient rule to take the derivative. All right. Next rule, kind of just going through a bunch of rules here. Next rule is the chain rule. All right, the chain rule is a very powerful rule. It gets used all the time. So let's talk about the chain rule. So we use the chain rule whenever we have a function f of x, and it is equal to, again, we're going to have components. We're going to have components g of x and h of x. All right. So whenever we have a function where where there is some outer function and then a function inside of it. So an outer function and an inner function. Whenever this is the case, we will use the chain rule. All right, the derivative of f of x using the chain rule is the derivative of g with respect to h times the derivative of h with respect to x. All right, now that perhaps can be a little confusing, um, but I think we can walk through it. I'll go through some examples and kind of show you what I mean. The chain rule is actually quite important, so I might just pause here and kind of explain it conceptually. So when we have the chain rule, what's going on here is there is some outer function, and then there's a function inside of it. Okay. And so when we do the chain rule, what we have to do is we have to take the derivative of the outer function first, and then multiply it by the derivative of the inner function. All right. And so that's where we follow this equation. Okay. Um, and actually, it's some kind of interesting intuition. If we want to know how does the function f change when x changes, whenever you have a function that is structured like this, then the derivative of f with respect to x is actually equal to the change in the outer function with respect to a change in the inner function times a change in the inner function divided by the variable, or I'm sorry, given a change in the variable. Again, this still might not be perfectly clear, but I'm kind of working my way towards it. The basic idea here is how does f change when x changes? Well, this is how it changes. First, we want to know how does g change given a change in h times how does h change given a change in x? So you kind of have to go through these two steps. It's kind of a two-step process. You take the derivative of the outer function and you multiply it by the derivative of the inner function. Now, in a generic math way, I can imagine that this isn't super interesting or potentially, for those who haven't seen calculus, a little bit a little bit unclear to be frank. But in economics, this is actually very powerful. And so I think once we get to economic applications in class, you'll see why these distinctions matter. All right. But for now, as we kind of touch on this from a purely math perspective, let's just move forward with some examples, and I think you'll see what I mean here. All right, so let's give an example of an equation. Here we go. Here's f of x. Here's some function. All right, I'm going to give you a simple example. 4x squared plus 2, and all of that is squared. All right, so there's a function. All right, and when we look at this, we can actually see that this is a function that's composed of two smaller functions. There's a g of x here, and there's an h of x. Okay, the g is this squared term. So here what we're doing is we're basically saying everything inside of the parentheses here, this is h of x. Everything on the outside of the parentheses, that's g of x. So h of x is 4x squared plus 2. And then the outer squared term here, the outer square, that is g of x. Okay, now if that's the case, then we can take the derivative just following the structure of the chain rule. All right. So let's take the derivative of the outer function. So the derivative of g first. So that's just 2. All right, put the same thing back inside. All right. So here's the derivative of the outer function first, kind of ignoring the inner function. All right. Times the derivative of the inner function, and that is 8x. Oh, whoops, sorry, it's not squared. So that's 8x. So there's our chain rule. So first, we take the derivative of the outer function. Here's the derivative of the outer function. This is the derivative of g with respect to h. And then here's the derivative of the inner function, the derivative of h with respect to x. Okay. So here's another way to kind of think about this that I think might be helpful. So let's go back and look at our function again. So here's our function, 4x squared plus 2 squared. Okay. Sometimes if we're working with chain rules, what we might want to do, especially early on to kind of be able to visualize what's happening here, is we can actually rewrite the function like this. Let's go ahead and just define h equals 4x squared plus 2. Let's define that. And if we define that, then we can rewrite this, and we can just call this h squared. Okay, so we have h squared. Then what we can do is we can take the derivative of that, right? So that's basically g. So basically g is equal to h squared. And so what we're doing here, the derivative of f of x with respect to x is equal to the derivative of g with respect to h times the derivative of h with respect to x. If I just take my h and I just replace it with the letter h, that actually might make it easier. And it's just much easier to see. The derivative is going to be equal to 2 times h times the derivative of h with respect to x. All right, and then we just plug it in. Well, what's h? Okay, let's plug in h. 2 times, what's h? It's 4x squared plus 2. So just plug that in. All right, times, what is the derivative of h with respect to x? Well, we can look at that, right? Bring the 2 down. 2 times 4, that's 8 times x. All right, 8x. So sometimes that can be kind of helpful in terms of using your chain rule. All right. So there, I think I will stop with the calculus review at that point. All right. I wish you the best of luck. I hope this is helpful. And yeah, let me know if you have any questions. All right. Thanks, everybody.